So we're going to try another area problem. This time, different function, different interval, but the exact same concept. We've got the parabola, y equals x squared minus 2x plus 2. We're going to find the area below the curve from x equals -1 to positive 2. We can see all that information in the graph. So the first thing, again, that we want to do is try to figure out what is our delta x value. We're going to start at -1 and go to positive 2. So the distance between these two is 3. That's final minus initial, or 2 minus -1, which is 3. So if we decided to use one rectangle, then the width of that one rectangle would be 3. If we decided to use two rectangles, then the width of each of those two rectangles would be 3 over 2. If we decided to use 4 rectangles, then the width of each rectangle would be 3 over 4. And if we decided to use 8 rectangles, then the width of each rectangle would be 3 over 8. So, of course, we're not going to use one rectangle, or 2, or 4, or 8. We're going to use n rectangles. So we're going to take that area, the interval of 3, we're going to divide that by n. So delta x is going to be found by taking the distance between our end value minus our initial value, or b minus a, divided by n. This is a very simple little formula, and it's going to be very useful throughout this unit. So delta x equals b minus a over n. In this case, b equals 2, and a equals -1. So our width is going to be 3 over n, and that width is constant throughout this problem. Okay, so that width will be the first thing that we need to find, that delta x value. That's going to kind of run the show for the rest of the problem. So to find the right endpoint of the first subinterval, we're going to take one step from -1. So we're going to take our first starting area of a, and we're going to add 1 delta x to get to our first right endpoint. And then we're going to take our 2 steps to get to our second x value, and we're going to take 3 steps to get to our third x value. So this is going to be -1 plus 3 over n. This is going to be -1 plus 6 over n. That's 3 times 2. And then -1 plus 9 over n. So generically speaking, if we take I steps, we're going to take a plus I delta x, in this case -1 plus 3i over n. And the reason we care about the x values, that's the first x value, the second x value, the third x value, the fourth x value, etc., is because each one of those x values determines the height of corresponding rectangles. So we've got our first rectangle, and our second rectangle, and our third rectangle, and our fourth rectangle, etc. And so we're going to use those x values to evaluate each one of those heights. So we're going to take the height of -1 plus 3 over n is going to be squared, and then we're going to minus 2 times that same -1 plus 3 over n, and then we're going to add 2. Where did that come from? That's our function over here. That tells us the height of each rectangle. So we can do that for each one of these, but the only one we really care about is the ith row. So we'll go ahead and jump down to there and say -1 plus 3i over n squared minus 2 times -1 plus 3i over n plus 2. So this entry right here and this entry right here are the height and the width of your generic ith rectangle. So when you multiply those together, you'll get the area of your ith rectangle. So what we're going to do is we're going to take the sum from I equals 1 to our generic n of the width times the height. And that height is a messy beast, but it is what it is. Let me just write that out. Let's see, we close that parenthesis and we close there. And again, this is the sum of the areas of the n rectangles. And we're going to let n go to infinity, and that's where the limit comes into play. The limit as n goes to infinity of the sum from I equals 1 to n of the width times the height of each of your rectangles. From here, it's a whole mess of algebra, but we just take it one step at a time. We will start off by expanding the expression inside the brackets. So we've got this binomial squared is 1 minus 6i over n plus 9i squared over n squared. Distributing this negative 2, we get a positive 2 minus 6i over n. And we still have a plus 2 right here. So that's going to combine a little bit, and we'll see that the I squared term is 9i squared over n squared. We've got two different I terms. They're both negative 6 over n, so that's going to be a negative 12 over n times, 12 over n times I. And then we've got some constants. We've got the 1 and the 2 and the 2, so that would give us 5. Then we can distribute the 3 over n into each of those things. And you get tired of writing the limit of the sum, but you get used to it. 3 times 9 is 27. 3 times 12 is 36. And 3 times 5 is 15. And if you're doing it right, then the degree of I is always going to be 1 less than the degree of n. So 2 over 1, 2 over 3, 1 over 2, 0 over 1. So for each one of these, we can evaluate the sum. So the limit as n approaches infinity of, the first one is going to be 27 over n cubed times the sum of I squared. That formula is n times n plus 1 times 2n plus 1 over 6. And then we've got negative 36 over n squared times the sum of the i's, and that formula is n times n plus 1 over 2. And then we've got 15 over n times n. 15 over n is being added up n times, so that's times n over 1. And when we take the limit of each one of these, we'll see that we've got a 27 times 2 over 6 for the first term. We've got a 36 over 2 for the second term, and we've got a 15 for the third term. Quick note, people tend to forget about this 2. That's this 2 right here. That shows up when you have your I squared summation. So people will miss that because it's hiding inside there, but don't forget it. So when we work this out, we get, let's see, well, these reduce. The 2 over 6 reduces to 1 over 3. So the 27 over 3 is 9. And 36 over 2 is minus 18. Then we get a plus 15. And when we work that out, we get negative 3 plus 15, which is 12. Which, no, that's not right. It's 9 minus 3. So it'll be 6, which is the final answer, which represents, again, the area bounded by the curve and those two vertical lines. The shaded region, this green shaded region, has an area of 6.